Hello students, welcome to the third lecture. So in this lecture we will try to look at a generalization of the Rayleigh quotient theorem that we discussed in the previous two lectures. Okay. So let's very quickly review what we were talking about in the last lecture. So if A is symmetric n cross n, we know it has n eigenvalues lambda 1 to lambda n, and we assume that they are ordered in ascending order from lambda 1 to lambda n. So lambda 1 is the smallest and lambda n is the largest. The Rayleigh quotient theorem states that the quadratic form x transpose ax normalized with x transpose x in the denominator lies between lambda 1 and lambda n. Right? In particular, if x is a unit vector, then the denominator is 1 and the quadratic form is bounded between lambda 1 and lambda n. So that's the main result that we talked about in the previous two lectures, right? And we looked at some consequences of this, and typically most of the corollaries seem to follow by actually trying to pick one particular x, right, such that x transpose ax is very easy to find. Okay, so it could be an x that's constructed from standard unit vectors, for example, or by some other means. Then if this quantity is very easy to compute, then that gives you naturally a bound on the smallest eigenvalue and the largest eigenvalue. So that's how we looked at a few applications of this theorem. Okay. What we'll try to do today is try to get a generalization of this. By the way, as I mentioned in the last lecture, another way to write this is to simply say that the minimum value of the Rayleigh coefficient is the lambda 1 and the maximum value of the Rayleigh coefficient is lambda n, right? Of course, needless to say, as I mentioned before, the maximum here is taken over all non-zero x, right? Because if x is 0, then this ratio is simply undefined, so you avoid that, right? In other words, here the minimum and maximum is unrestricted pretty much, right? The minimum is taken over all x pretty much, right? The whole n-dimensional space, right? So x is in the complete n-dimensional space. Here also x is in the n-dimensional space, of course excluding the zero vector. Okay. So a natural question to ask is, well, this gives me a variational characterization of the smallest eigenvalue and the largest eigenvalue, no doubt, right? But what if I want the second smallest eigenvalue or the third smallest eigenvalue, right? So is it possible to give a variational characterization of lambda 2? Meaning, can I say the lambda 2 is the minimum of the Rayleigh coefficient or the maximum of the Rayleigh coefficient or some such thing, okay? So that's what we'll start the investigation from. Okay, so let's very quickly recall the proof of this, right? How did we end up proving this? All we did is we wrote the Rayleigh quotient by making a change of the variable, right? So we substituted y equal to q transpose x, if you remember correctly, where the columns of q were the eigenvectors of the matrix A. Okay. So the columns of Q were V1 to Vn, where V1 to Vn are the eigenvectors of the matrix A. Okay, so Q is simply the eigenvector matrix of A, right? We made a change of variable y equal to Q transpose x, and in terms of y, this Rayleigh coefficient is actually extremely simple. All it becomes is summation of lambda I yi square by summation of yi square. Okay, that's what it became. The summation is over all I equal to 1 to n, right? This is what it was, as we saw in the very first lecture of this segment, right? And we said that to minimize it, so effectively, if summation of yi square is 1, then the denominator just becomes 1, and the numerator here just reduces to summation of lambda I yi square, right? And we said, well, if you want to minimize it, then I simply set y1 to be 1 and all the other y's to be 0. Okay, that will give you lambda 1, and if I want to maximize it, then I'll simply set yn to be 1 and all the other y's to 0. That will maximize it, right? That's what we did. Now if I want to get lambda 2, right, the natural thing to do if I want to get lambda 2 will be to somehow force, in addition to this constraint, somehow try to force that y1 is also 0, right? If y1 is 0, then the summation simply becomes lambda 2 y2 square plus lambda 3 y3 square and so on, right? The lambda 1 y1 square term will be missing, okay, because y1 is forced to 0. Okay? In that case, if I have to minimize this sum, I have no choice but to set y2 to 1, right? and all the other y's to 0. Okay, so that's the main idea. So what I'm going to do is I'm going to set y1 to 0, right? And what is y1? Remember, just by the definition of y is q transpose x. So y1 is simply going to be the dot product of the first row of q transpose with x, right? Well, the first row of q transpose is simply the first column of q, right? So that's v1, so dot product of v1 with x, right? So setting y1 equal to 0 is the same as saying that my vector x must be orthogonal to v1, the first eigenvector of the matrix. Okay. Oops, it seems I have notes out of order here. Never mind. Okay, so that's what I'm going to do. Okay, so I'm going to construct the Rayleigh coefficient x transpose ax by x transpose x, but I'm only going to consider the Rayleigh quotient over those x, right, that are perpendicular to v1, the first eigenvector. Okay, so in some sense I'm going to minimize the Rayleigh coefficient not over the whole space but only over the vectors that are perpendicular to the first eigenvector, right? And of course, once again, I just have to exclude the 0 vector because the Rayleigh coefficient is not defined at 0. Okay, so this is what I will try to do. I'll try to minimize the Rayleigh coefficient over this space, not Rn, not the whole n-dimensional space, right? In fact, what is the dimension of this space? The space of all vectors that are orthogonal to the first eigenvector. It's an n-1 dimensional space. Right, it's an n-1 dimensional space. So I'm going to minimize the Rayleigh coefficient over this n-1 dimensional space. Right. So this makes sure that any x I consider from this space will not have any component along v1. So it's as if you have completely forgotten about v1, right? You have sort of eliminated that direction completely from consideration. Of all the remaining directions, the direction that has the smallest amplification is obviously v2, the second eigenvector. Right, that's why this quantity is going to evaluate to lambda 2. Right, so when you minimize it, you will actually get the second eigenvalue. That is clear, right? So I urge all of you to go back and look at the proof and make sure that this makes sense. Right, now all we are saying here is that if I have to look at the direction that has the smallest amplification, that is lambda 1, that is v1, and the corresponding amplification is lambda 1. If I have to look at the direction that has the second largest amplification, right, by only focusing on the directions that are orthogonal to v1, then you will get v2 to be the smallest, right? Similarly, if I take the minimum of the Rayleigh coefficient over all x that are orthogonal to both v1 and v2, what should I get? That should give me lambda 3, the third smallest eigenvalue, right? Because I am completely forgetting about the directions v1 and v2. Among the remaining directions, right, x here will not have any component along v1 and v2. It will only have components starting from v3, v4, v5, right? So if you write x in terms of v3, v4, v5, you will see that the smallest value that it can have is only lambda 3 because that is the smallest eigenvalue. Okay, so this gives you in some sense, a variational characterization of all the eigenvalues, right? So in fact, you can also get lambda n, correct? So here, by the way, here you are actually minimizing on an n-2 dimensional space, not an n-1 dimensional space, right? Similarly, to get lambda, let's say lambda 4, you'll be minimizing over a n-3 dimensional space, right? In general, to get lambda n-1, you will be minimizing over an n-1 dimensional, you will be minimizing over a 1 dimensional space, correct? Because you want x to be orthogonal to v1, you want x to be orthogonal to v2, you simply want x to be orthogonal to even vn-2, right? So here this is going to be essentially a 2-dimensional space. Okay, that will give you lambda n-1. So in general, to get lambda k, you have to minimize over all x that are orthogonal to v1, orthogonal to v2, orthogonal to vk minus 1. Okay, x transpose ax by x transpose x, right? And this happens to be an n minus k minus 1, that is n minus k plus 1 dimensional space. Okay, so you have to minimize over this particular n minus k plus 1 dimensional space to get lambda k. Okay, I hope that's clear to everybody. By the way, what happens if you maximize instead of minimizing? So let's say I want to maximize the Rayleigh coefficient x transpose ax by x transpose x over all x that are orthogonal to, let us say, the last eigenvector Vn. Right? Of course, x not equal to 0. Let's assume that let's assume that this is always there. Okay, from next time I'm not going to write this. Right? So maximize x orthogonal to the largest eigenvector. What would you get? You would actually get the n minus 1th eigenvalue. Okay, because if I were to maximize it over the whole n dimensional space, I would get lambda n. That's the Rayleigh quotient theorem, right? But now, if I force x to be orthogonal to Vn, the largest eigenvector, okay, or the eigenvector with the largest eigenvalue, then Vn is completely dropped from the picture, right? So this x basically will only have terms involving V1 to Vn minus 1. Right? Now when I try to maximize it, naturally I'll get lambda n minus 1. Okay, this is effectively like saying yn is 0. If you make a change of variable to y, it's effectively like saying yn is 0. Okay, so the maximization of this is going to give you lambda n minus 1. So basically lambda k, once again, is going to be given, can also be written as a maximization. You can write it as a maximization of x orthogonal to Vn, x orthogonal to Vn minus 1, so on, x orthogonal to Vk plus 1, okay, x transpose Ax by x transpose x. Okay, so here the number of vectors here, you can see there is n minus 1, you are going all the way up to n minus k plus 1. Correct. So this effectively is going to be a k-dimensional space. Okay, because you are taking all the vectors that are orthogonal to n minus k plus 1 vectors. You are going to get orthogonal to n minus k vectors. I'm sorry, you are going to get a k-dimensional space. Okay. Okay. So that's going to be lambda k. Lambda k is going to be the maximum. Okay. So basically, you can write each eigenvector either as the minimum of a Rayleigh coefficient over some space, or the maximum of the Rayleigh coefficient over some space. Okay? And the dimension of the space will depend upon the the value of k. Okay, and whether you are choosing to minimize or maximize. Okay, so I hope this is clear to everybody. Okay, so this is the main idea. It again follows from the basic idea about what eigenvectors and eigenvalues are, and by making a change of variable for x in the Rayleigh coefficient. Okay. So now let us try to see if we can do similar applications of this like we did for the Rayleigh quotient theorem, right? So remember, just recall, how did we apply the Rayleigh quotient theorem, right? We simply looked at how did we apply the Rayleigh quotient theorem, right? We simply looked at typical x for which the Rayleigh quotient is very easy to find, and then you get a bound on lambda 1 and lambda. That's what you do, right? So here also we can try to do something very similar, maybe, right? I can try to find an x, okay, such that x is orthogonal to v1 and the Rayleigh quotient is easy to find for that x, right? Then that will give me a bound on lambda 2, right? That's how it would work, is it, right? So I will try to find an x that's orthogonal to v1, and maybe for that x the Rayleigh quotient is easy to find, and that gives me a bound on lambda 2. But that is a very huge ask, right? Simply because finding an eigenvector is not very trivial. At least by inspection of a matrix, you may not be able to say what the first eigenvector is, right? So the utility of this is a bit limited in that sense, right? Mainly because the space on which I am minimizing includes or needs knowledge of the first eigenvector. Okay? So let me try to get rid of that limitation and see what happens, right? So here I am minimizing the Rayleigh quotient over this particular n-1 dimensional space that is orthogonal to v1. Okay? Let me see what happens if I minimize the Rayleigh coefficient over an arbitrary n-1 dimensional space. Okay? Pick any n-1 dimensional space S. Okay, and let's try to consider the minimum value of the Rayleigh coefficient on this space. Now, the important thing to note here is that I'm not putting any restriction on S, right? S can be anything, and let me try, and the only thing is S has to be n minus 1 dimensional. That's the only restriction I'm putting, right? So in this scenario, let us try to consider the minimum value of the Rayleigh coefficient. Okay, of course the answer will depend on S. For example, if S is the space orthogonal to V1, okay, then we already know what the answer is, right? If S is a space orthogonal to V1, then the answer is going to be lambda 2. The minimum value is going to be lambda 2, right? No question about it. Okay? Now, of course, as I said, S here is arbitrary because we don't often have knowledge of V1. S is arbitrary. That means that the space here, the x in this space, the vectors x in this space, may have some component along V1 as well. Okay? Let's take an example. So suppose that n is 2, just an illustrative example to understand what's going on. And let us say that, my first eigenvector v1 is nicely like this, it's horizontal, and the second eigenvector is vertical, as in like this, right? Doesn't look good, maybe draw it. Okay, the second eigenvector. Okay, so these basically v1 is a unit vector in the horizontal direction, v2 is a unit vector in the vertical direction, right? And let us say my space S here, because n is 2, S has to be a one-dimensional space, correct? N minus 1, so it has to be a one-dimensional space. So let us say that the one-dimensional space is just, this space. Okay, we draw it. Okay, anyway, you get the idea. So let's say this is my one-dimensional space S. Okay, so as you can see, every vector in S, right, is essentially a span of v1 plus v2, is it not? Okay, v1 is your I bar and v2 is your j bar, for example. Every vector here is like, I plus j, 2i plus 2j, 3i plus 3j, so on. Those give you all the vectors in this one-dimensional space, is it not? Right? So let's try to find the minimum of the Rayleigh coefficient on this space, okay, on this one-dimensional space. Okay, so if I try to find the minimum of the Rayleigh coefficient on this one-dimensional space, what do I get? Okay, so what do I do, right? So let us try to pick. So what I can do is I can try to pick a unit vector in this one-dimensional space. So let me try to pick a unit vector in this one-dimensional space. This one-dimensional space, I mean. And let me compute the Rayleigh coefficient, right? So in fact, there are only two unit vectors in this space, right? I mean, there's one unit vector over here and another unit vector over here, correct? And this unit vector is simply v1 plus v2 by square root 2, right? Even v1 and v2 are unit norm, right, as usual. And this unit vector is minus v1 minus v2 by square root 2, right? So you can find the Rayleigh coefficient for both of these. In fact, for both of them, the Rayleigh coefficient will evaluate to be same, right? Because one vector, this unit vector is essentially negative of this unit vector. So when you replace x with minus x, the Rayleigh coefficient doesn't really change, right? Because it's So basically you can just evaluate it in this way, right? So let's try to find the Rayleigh coefficient at this value. Okay, so what will you get? You will get v1 plus v2 by square root 2 transpose a times v1 plus v2 by square root 2. I don't have to write the denominator because this is a unit vector. Okay. Now I expand this and I leave it to you as an exercise to do. Remember, v1 and v2 are eigenvectors of it, right? A v1 is lambda 1 v1 and a v2 is lambda 2 v2, right? So with that knowledge, you can simply expand this and do all the mathematics. And what you will get is lambda 1 plus lambda 2 by 2. Somebody correct me if I'm wrong, but you'll get lambda 1 plus lambda 2 by 2. Okay, so you can see that, and you can say that the Rayleigh coefficient for this unit vector is then going to be lambda 1 plus lambda 2 by 2. It's the average of lambda 1 and lambda 2, right? Now similarly, if you take any other vector on this line, the Rayleigh coefficient will be the same, okay? Because any vector on this line has the same unit vector. Right? This is a unit vector corresponding to any vector in this line, right? So if I pick some other vector here, then you will again get a numerator and the denominator, they will cancel, and ultimately you will get lambda 1 plus lambda 2 by 2. That's very easy to check, right? So basically what we are trying to say is that for any vector on this space, the value is this, or the Rayleigh quotient. That means the minimum must also be this, right? So for this space, the minimum happens to be lambda 1 plus lambda 2 by 2. In other words, the average of the two eigenvalues, lambda 1 and lambda 2. Okay, so just to recap, what I am trying to say here is that if you pick your S to be orthogonal to V1, meaning let us say if you had picked your S like this vertically, if your S was like this vertically, right, then the minimum value of the Rayleigh quotient would have been lambda 2, right? If you pick your S like this, as a 45-degree angle, then the minimum value happens to be the average of the two eigenvalues. Okay? In fact, if you pick your S to be, let us say, horizontally, pick this to be my S, can somebody guess what the Rayleigh quotient will be? Right? The unit vector is clearly V1 here in this space, so the Rayleigh quotient will just be lambda 1. Okay? So you can see, by picking many different one-dimensional spaces, if you pick it horizontally, you will get lambda 1. If you pick it vertically, you will get lambda 2. If you pick it anywhere else, you will get some combination of lambda 1 and lambda 2. Okay, like this. Some combination of lambda 1. Okay. So here you got the average of lambda 1, right? So just to illustrate this on the number line, so just to make it clear, you have lambda 1 here, lambda 2 here. Lambda 1 is a smaller eigenvalue, right? For one particular choice of S, I am getting this to be the minimum of the Rayleigh quotient on the space. For another choice, I am getting this to be the minimum of the Rayleigh quotient. For some other choice of S, I am getting the Rayleigh quotient to be in between, right? And it's not a leap of imagination to say that if I had to pick a different S, that's, let's say, something slightly oblique, like this, right? You will get a Rayleigh quotient that's somewhere here, okay? And similarly, if you pick your subspace S to be like this, then your Rayleigh quotient will be here. In any case, you will essentially, by changing the subspace S, you will sweep all the values between lambda 1 and lambda 2. Okay? So this is what you can actually write. You can say that the minimum of the Rayleigh coefficient is between lambda 1 and lambda 2. Okay? If S is an n-1 dimensional space, that's the key here. S is an n-dimensional. The example I gave here is for n equal to 2, but you can actually make a legitimate argument, a similar argument even when n is higher than 2. Okay, so the minimum of the Rayleigh coefficient. So basically what I am saying is, if this space S was the space that is orthogonal to V1, then this value would have been equal to lambda 2. Okay. By removing that assumption, because we do not really know what V1 is often, by removing that assumption, by making X to be in an arbitrary space S of dimension n-1, you may not get lambda 2, but you will definitely get something that is between lambda 1 and lambda 2. Okay, right. So that's the main idea here. Now, what if similarly, if you can actually take the subspace S to be an n-2 dimensional space? If S is an n-2 dimensional space. Okay. Remember, if S is the n-2 dimensional space that is orthogonal to both V1 and V2, then this value would have evaluated to lambda 3. This is what would have evaluated to lambda 3. Right? Now it will be between lambda 1 and lambda 3. Right? If S is an n-2 dimensional space, if it is orthogonal to both V1 and V2, then it will be equal to lambda 3. But if, let us say, it has a component along V1 or along V2, then the minimum value could actually be lower. It would get as low as lambda 1. For example, if your space S includes V1, then it will actually be, the minimum value will actually be lambda 1. Okay. So this is the idea behind. Now you can actually generalize this, of course, right? To write lambda k. So suppose if I do minimum of X in any subspace S, X transpose AX by X transpose X, right? and the minimum value will be between lambda 1 and lambda k if S is an n minus k plus 1 dimensional space, right? So for k equal to 1, right, for k equal to 1, you get your Rayleigh quotient theorem back, because if k is 1, then this just becomes n. So the minimum in an n dimensional space, that is just lambda 1. Okay, it sort of fits. If k is 2, then you get back this result over here, right? If k is 2, then n minus k plus 1 becomes n minus 1, and you get back this result. If k is 3, you get this result, and so on. This is the most general form of that result, right? So basically what it is saying is, if you consider the minimum value of the Rayleigh coefficient on a subspace, not on the whole space, you consider the minimum value of the Rayleigh coefficient on a subspace, right, that is bounded between the smallest eigenvalue and another eigenvalue, okay? Which eigenvalue depends on what is the dimension of the space. Okay, if you take the whole n-dimensional space, and this is lambda, then this is just going to be lambda 1, both are going to be lambda, right? But if you pick, for example, if you take k to be, like, let us say n, right? Then let's say you are minimizing only over a one-dimensional space. Then it could be lambda 1 to lambda n. Because if S were a one-dimensional space, S could actually be the space along Vn, the largest eigenvalue, in which case this would evaluate to lambda n, right? Or S could be the space along V1, in which case it would evaluate to lambda 1. Okay. So the dimension of the space decides the upper bound. Okay. This is the main identity that I wanted to talk about in this lecture, right? Similar thing can be done even when you are maximizing. Remember, all this is assuming we are doing the minimization. Even when we are doing the maximization, you could actually get a very similar result. Okay, so for example, let me just write this down and let me ask your opinion about this. Suppose if I want to maximize x, okay, maximize the Rayleigh coefficient, okay, when x is in n minus 1 dimensional space. Okay, S is in n minus 1 dimensional space, right? So S is in n minus 1 dimensional space, and we want to maximize x transpose Ax by x transpose X. Okay. So what could be the smallest and the largest value of this? Any ideas? Right? So if I want to get the largest value, right? So what I have to do, the largest value, in order to get the largest value, I need to allow x to be Vn, the largest eigenvector. Okay. So if I pick S to be, let us say, the space spanned by V2, V3 to Vn. Okay, this is an n minus 1 dimensional space. Then I will get the maximum value to be lambda n. Okay, is it not? Okay, it's certainly possible for the maximum to be lambda n. Okay, by taking S to be the span of these vectors V2 to Vn, right? But suppose if I want to minimize it, right? To minimize it, I want to avoid Vn as much as possible. Okay, so if I take S to be the space that is orthogonal to Vn, okay, so space take X orthogonal to Vn. Okay, that also gives me an n minus 1 dimensional space, and in that case, the maximum will be lambda n minus 1. Okay, that's what you will get. Okay, so in general, you can write lambda k less than or equal to max of x in S, x transpose Ax by x transpose x, the Rayleigh coefficient less than or equal to lambda n, if S is a k dimensional space. Okay, if S is the k dimensional space, the maximum as far as the Rayleigh coefficient goes happens when S includes Vn, in which case it will be lambda n. The minimum happens when S completely avoids the top eigenvectors and only settles on the bottom k eigenvectors, in which case it will happen to be equal to lambda. Okay, so these set of results, this is the second one and the first one that I talked about here. Okay, they are called the Courant-Fisher min-max theorems. Okay, let me just try to write down both of them next to each other. Okay, or anyway, let me just rewrite it. Okay. faster. Cohen-Fisher min-max theorem. Okay, I'll tell you why it's called the min-max theorem in a minute. Okay, what it tells you is basically what we just wrote down here, right? Minimum value of the Rayleigh coefficient is between lambda 1 and lambda k for any if S is n minus k plus 1 dimensional, and the maximum value over any subspace if S is k dimensional. Okay, these are called the Cohen-Fisher min-max theorems. Okay, so now let me rewrite these statements slightly, just like we rewrote the the Rayleigh min-max theorem, the Rayleigh quotient theorem, right? Remember, we had some quantity here in between some bounds, so we can easily say that the value here is the maximum value of this, the value here is the minimum value of this, right? Similarly, the value here is the maximum value of this, and the value here is the minimum value of this, right? If you do that, you'll actually get something very cute. You'll write like min max x in S is k dimensional of the Rayleigh coefficient is equal to lambda. Okay, I just wrote one of the four things that I said, right? The maximum value of this is equal to lambda n, the minimum value of this is equal to lambda k. So sorry, it has to be lambda k over here. Okay, so I just wrote this part here. Okay, because of the involvement of min max here, it's called the min max theorem. Okay, of course, if you write here, you'll actually get max min, you'll also get a min min and a max max. Okay, but one can actually say that this is the strongest part, everything else can be derived from this and so on and so forth, right? So this is called the Cohen-Fisher min-max theorem. Okay, fine. What is the use of this? Well, just like the Rayleigh quotient theorem, right? If you are able to find a subspace for me such that this value is easy to evaluate, okay? If you are able to find a subspace for which this is easy to evaluate, then I get a bound on lambda k, right? The kth smallest eigenvalue. Okay, or if you are able to find a subspace S such that this is easy to evaluate. Remember, the constraint is on the dimension of the space, right? If I am able to find a k dimensional space such that this is easy to evaluate for me, then that gives me a bound on lambda k, the kth smallest eigenvalue. So this can be used to find bounds on the other eigenvalues as well, not just the smallest or the largest eigenvalue. Okay, for example, hypothetically, let us say that suppose there exists a subspace, right? Suppose there exists a subspace S of size k, okay, of dimension k, sorry, not size, of dimension k, okay, such that x transpose Ax on this subspace, the Rayleigh coefficient is at least, let us say, 1. Okay, on this particular subspace, I know that the Rayleigh coefficient is always at least 1. Okay, I know that, it's been told to me, right? Okay, then what do I know, right? I know that the minimum on this subspace, okay, so the minimum of the Rayleigh coefficient, let me just say Rayleigh coefficient, right? The Rayleigh coefficient of x is at least 1, and the maximum is also at least 1, right? At least 1, I know that, correct? So here a subspace S is k dimensional subspace, right? So what does that tell me, right? So first of all, it will tell me if I apply, let's say you have two things to apply here. Let's say apply the second, right? I know that the maximum of the Rayleigh coefficient is at least 1. So I know the maximum is at least 1, right? So maximum is bigger than or equal to 1. Okay? I know that. Okay. So what does that tell me? That tells me immediately that lambda n is bigger than or equal to 1. Okay. So the first conclusion that you can make from this is that lambda n bigger than or equal to 1. Well, you can say that's quite trivial, because I could have concluded the same thing even from the Rayleigh quotient theorem, right? There is some x for which the Rayleigh quotient is bigger than or equal to 1. Of course, here you are given more information. You are given that for every x in the subspace, Rayleigh quotient is bigger than or equal to 1. And that's immaterial. As long as there exists an x in the subspace for which Rayleigh quotient is 1, the largest eigenvalue is bigger than or equal to 1. So this inequality is actually not giving you much. But let us try to apply this inequality. Okay. I know that the minimum value of the Rayleigh quotient is also at least 1, right? What does that mean? That means that this quantity over here is at least 1. Okay. That means whatever ends up on the right side also must be at least 1. Okay. Now let us be very careful about what ends up on the right side. Remember, the subspace S is given to be of dimension k, right? Subspace S is dimension k. So if the subspace S is n minus k plus 1, what you get here is lambda k, right? But if the subspace S here is k, then what you will get on the right side will be lambda n minus k plus 1. Okay. The second conclusion you can make is actually lambda n minus k plus 1 is bigger than or equal to 1. Okay. So as you can see, you are able to make actually a much stronger conclusion here, right? This is the conclusion you would get if you apply just the Rayleigh quotient theorem. This is the conclusion you will get if you apply the Fisher-Min-Max theorem, right? What it is telling you that if on the subspace, if there exists a k-dimensional subspace on which the Rayleigh quotient is 1, definitely at least 1, then the kth eigenvalue from the top, this is like the kth eigenvalue from the top, also must be at least 1. Okay? Fine. In the next portion, I will look at a very popular application of this, is what is called the interlacing theorem. So one word of one note that this lecture is slightly more advanced than the previous lectures and even the rest of the course. Okay, so if you have any confusion, please rewatch the lecture or see the notes, or maybe postpone seeing this lecture till the end of this segment. That is also fine. Okay, because we may not use most of these things. The previous two lectures, Rayleigh quotient, we'll definitely use, but this we may not use the rest of the segment, in spite of the fact that this is actually an extremely powerful result.